Biorefinery System Module 10 Lignocellulose Biorefinery Engineering Part 2 Segment 2 Food and Animal Feed. With me, Yusuf from Bioengineering Study Program, School of Life Sciences and Technology, Institut Teknologi Bandung. Previously, we have discussed about bio-based materials. In this segment, we will discuss about food and animal feed. Xylose is a type of pentose that is soluble in water and some organic solvents like hot ethanol, while insoluble in diethyl ether. Xylose often exists as a colorless or white crystal powder that tastes sweet and refreshing. It exists in the form of polysaccharide in plants, especially in product waste like straws and ears of rice. Xylitol is produced by catalytic hydrogenation from xylose. Xylitol is widely used for food additive due to its outstanding features like anti-caries properties and because it can be used by diabetics. Xylitol is a type of sugar alcohol that exists widely in vegetables and fruits in nature. Main technology for xylitol production is microbial conversion, in which microorganisms convert xylose into xylitol by xylose reductase within the microbial cells. There are several advantages of the microbial conversion technology. First, it has a high utilization ratio of raw materials. The chemical method uses only pure xylose as raw materials, thus the xylose in const-over hydrolysis cannot be used. Second, the bioconversion process can reduce the environmental pollution because in this process raw materials are directly used without pre-treatment. Third, bioconversion consumes less energy. In the bioconversion process, xylitol is produced through one-stage concentration and crystallization, thereby decreasing energy consumption. Fourth, the bioconversion process needs simpler devices. In the bioconversion process, the main devices are simple reaction tanks and a few fermentation cylinders. Fifth, the process is safe and easy to operate. Bioconversion is processed under normal temperature and pressure without asepsis operation. Sixth, the process can provide better products. The products are more suitable for food processing because the whole process avoids contact with metal power catalysts. The screening and optimization of nutrients and the foundation of new routes are the key problems for xylitol production in the future. Vanillin is a white to faint yellow crystalline powder or a sickle crystal. The melting point of vanillin is 80 to 81 degrees C and the boiling point is 285 degrees C. Vanillin is slightly soluble in cold water but dissolves well in ethyl alcohol, diethyl chloroform, glacial acetic acid, and pyridine. Pure vanillin is mainly extracted from the pods of vanilla and the yield is too low to satisfy market demand. Biovanillin produced from the natural precursors of vanillin by microorganisms could displace natural vanillin. Vanillin is widely applied in industrial production. For example, it is used as a perfume or perfume fixing agent in food, toothpaste, fancy soap, and tobacco. Vanillin is also an important intermediate material in pharmaceutical chemicals. Additionally, vanillin can be an auxiliary material in chemical engineering, an anti-hardening agent for plastics, and an electroplating brightening agent. In agriculture, vanillin can be used as a yield-increasing agent or ripening agent for sugarcane, as well as a material for the preparation of herbicides and insect attractants. A large demand for vanillin has arisen due to the high value that many countries put on food security. As a rough estimate, the yield of vanillin worldwide is around 5,000 to 8,000 tons, and the demand exceeds supply by 3,000 to 4,000 tons. Vanillin production via the bioconversion method has been developed for more than 10 years, and this technology made use of multiple biological materials including fungi, genetically engineered bacterium and extracted enzymes. For the time being, there has been no report on the multiple industrialization of vanillin. The most studied bioconversion method is a two-stage technology, where vanillic acid is produced from ferulic acid and then vanillin is further prepared from vanillic acid. Animal feed. The degeneration and desertification of grassland lead to the shortage of animal feed of high quality, while the development of large-scale farming practices calls for a large amount of animal feed. At present, research is centered on the methods of microbial fermentation and sealing and ammoniating to treat straw, and these measures cannot realize the efficient conversion of crop straw to feedstuff of high quality and high nutritive value. Corn stalk is the main source of traditional feedstuffs, but its application is limited due to its high C to N ratio. Recent methods have shown steam explosion coupled with ammonia pre-soaking can significantly increase the nitrogen content of straw, and the recycle cost is high even though the ammonia can be reused. Research into silage feed started years ago, and sealing is a process coupling anaerobic fermentation and acidifying, during which the soluble sugar and protein contains are low, which is unfavorable for animal consumption. Adding cellulase during the unsealing process can increase the soluble sugar and organic acid contents during the fermentation. In this way, lactic acid fermentation and the saccharification process are synchronized by adding lactic acid bacteria and hydrolase. The soluble sugar produced from enzymolysis can be used by lactic acid bacteria, and the growth of lactic acid bacteria can inhibit the growth of other microorganisms. However, the enzyme cost is high in this process. To solve the problems, a method of in situ fermentation coupled with unsealing has been proposed. The results show that both cellulose and hemicellulose were produced during the fermentation. The nitrogen content increased from 6.7% to 14.7% after fermentation, and the cellulose degraded by 38% and hemicellulose by 21%. For the next module, we will discuss about lignocellulose biorefinery process engineering. Until then, I am Yusuf from Institut Teknologi Bandung.